So it's time for us to combine everything that we've learned, and the first application is for us to use our knowledge to sketch the graphs of slightly more complicated looking functions. So for example, you might be asked to sketch the graph of f of x is equal to negative 2x squared plus 32. So let's just unpack what is happening. What does this function do? So first of all, this function takes my input and it squares it. And the moment you see that, you need to be thinking, okay, basic shape parabola. We saw that the moment you have a situation of y is equal to x squared, you're going to have a parabolic shape for your graph. And these other parameters will just modify it slightly, but fundamentally you're going to have a parabola as your graph. And so after you've squared the input, the next thing you do is you times it by negative 2. So we saw that that has a flipping effect on my graph. So we're starting out with y is equal to x squared, and then we're saying, okay, take all of those outputs and multiply them by negative 2. So you end up with something that looks like that, and is a bit narrower actually, if I'm to be a bit more accurate. So let's make that narrow and stop being lazy. And then you're adding 32 to all the outputs, so your graph moves up by 32 units. So ultimately your final sketch looks like this. And very important that a sketch is not a plot. You do not calculate individual points and join them. That is plotting a graph. Sketching is reasoning about the various parameters of the function that are affecting what its graph is going to look like. The way that I've done now, unpacking what does the negative 2 do to the graph? What does the plus 32 do to the graph? So anyway, you end up with something potentially that looks like, let's say like that. And the first label you can put on your graph straight away is this guy over here. Even though it doesn't look like my turning point, I've done a very bad job of sketching my graph. In fact, the pedantic side of me is going to try and get this right. So we want our turning point to be over there, right? Because what's happened is it's gone from, so y is equal to x squared, my turning point was over here, and then the negative 2 happened, so then it just turned around like that, but it was still on 0. And then moving it up by 32 means it now sits over there. So the first point I can label is that turning point. The x coordinate is 0, the y coordinate is 32. And ordinarily you wouldn't have to label the turning point. It's because it just so happens to coincide with the y-intercept of the graph. That's what makes it important to label. So you need to label the y-intercept of the graph. Another way that you could have worked out the y-intercept of the graph is, we know that by virtue of it being a y-intercept, its x-coordinate is definitely 0. So the question we're asking ourselves is, when the input to my function is 0, what is the output going to be? So if I look at my function now, I'm going to have negative 2 times 0 squared, so that term just disappears, and all you're left with is 32. So that corresponds with the answer that I had written in the first place there. And then the next thing we're interested in is those guys, the x-intercepts. And what we know about them straight away is that their y-coordinates are 0. So what we're asking ourselves is, what inputs are going to give me an output of 0? So I want my output to be 0. So minus 2 times some input squared plus 32 needs to give me 0. Of course, this is a quadratic function, so solve it like a quadratic function. The question would be, how do I factorize an expression like this? Because this side is already 0, so that's already taken care of for us. So what I would do over here is I would factor out a negative 2, and I'd be left here with x squared minus 16. And of course, that very conveniently gives us a difference of 2 squares. So x minus 4, x plus 4 is equal to 0. Obviously, negative 2 can't be equal to 0. So the null property is going to tell us that one of those two must be equal to 0. So either x minus 4 must be equal to 0, or x plus 4 must be equal to 0, which would mean that either x is equal to positive 4 or negative 4. So that's another way that you can, yeah, okay, cool. So x is positive 4 or negative 4. Obviously, this would be the negative 4, and that would be the positive 4. And voila, you have sketched your graph. Important thing that I want to talk about quickly over here is, well, there are three things. No, there's two things. Okay, so something that you might be asked commonly about your parabola is what is its axis of symmetry? So this is something we touched on as well last term. But axis of symmetry is just basically the mirror line. As you can see, the parabola has a beautiful symmetric shape, and so in our case, the line of symmetry is going to be the y-axis. But of course, it's usually not adequate to say the y-axis. You need to give the equation of the axis of symmetry, and the equation of the y-axis is x is equal to 0. All along here, x is equal to 0. If you pick any point on the y-axis, its x coordinate is 0. Hence the equation x is equal to 0. So that would be your answer if you were asked what is the axis of symmetry of a parabola. The other important thing that I want to talk about very quickly is the idea of domain and range. So when we talk about domain and range, well, no, we're going to talk about them one at a time rather. So domain is simply all the losing words. So domain is all the values that are allowed as inputs for your function. And so for a lot of functions, well, okay, I don't know about a lot, but for a lot of functions that you're going to encounter, the domain is typically going to be, any real number, really. So if you look at, for example, this, oh dear, there goes my whole entire function. If you look at this function over here, it has no discrimination about which inputs are allowed. You can square any number that you so desire. You can square 0, you can square 9, you can square, you can square any number, 0,5, -2, all those numbers can be squared. So how we write that is that the domain of this function is any real number. X is an element of the set of real numbers. So that's how you would write that. When you talk about range, we're talking about or the set of a particular function's outputs. So what are the possible outputs of this function? And this is where one of the places where it's so glorious and beautiful to have the option to visualize a function using a graph. Because if you look at this graph, for example, the graph of the function y is equal to -2x squared plus 32, what you can see is that your outputs, they're capped at 32. This is, as big an output as you can get from this function. There's no higher output happening, so if you look at inputs going further and further this way, they're just getting less and less and less, smaller and smaller and smaller, their outputs. And likewise, the more you go this way, the higher your input is, the lower your output ends up being. So you can see that the outputs of this function, they increase, and then they're capped at 32, and then the more your input goes this way, the more your output goes downward, it decreases. So the way that you would express the range of this function, you would say that the range of this function is, and you can use f of x because f of x represents output, or you could use y. You'd say that f of x is smaller than or equal to 32. It doesn't go beyond 32. So 32 is the maximum output of this function, no more. or likewise y is less than or equal to 32. So just go with whatever notation, function notation you've been given in the question. So in this case, we've been given f notation, so you wouldn't use that, preferably not. Rather use that. Stick with whatever you've been given. Let's look at another example. Oh, I can just go to another page. How exciting. So let's say we're asked to sketch. Okay, sketch the graph of y is equal to a quarter to the power of x minus 1. So again, think about what's happening here. What is this function doing? This function says, for whatever input you have, take a quarter and raise it to the power of that input. And again, ding, 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 I'm raising some number to the power of my input. That is an exponential function. It's very important to be able to identify these things, because then you can load the correct image for a basic shape to work with. So you have an exponential function, so you're looking at something that does that. But now, remember that the base affects the direction of your graph. So because it's a number between 0 and 1, it's not going to look like that. It's going to look like that instead. Okay, that was terrible. Something like that. Okay, it's going to be a decreasing function. So that's the first thing that's happening there. And then next, we're looking at what that minus 1 means. So it means that all of my outputs are being decreased by 1. So what's going to happen now is that my graph is going to look perhaps something like that, right? And notice that my asymptote has moved. It's no longer on the x-axis, it's now on -1. And it's very important to label that. So that number, very important to write down. And if they were to say, what is the asymptote of this function, then the answer would be y is equal to -1. That is the asymptote. And if you get confused about, when is it y is equal to something, when is it x is equal to something, think about what is constant on that line. So as I move along this line, my x coordinates are changing, but my y coordinate is staying the same. So that means my equation is going to be y is equal to -1. So that would be the equation of the asymptote. And then, of course, we want to then figure out what the coordinates of these two are, the x-intercept and the y-intercept. So let's just clear up some space over here. So the x-intercept, we're going to have, we know that the y coordinate is 0. So we'll write that down so long. And so we're asking ourselves, for which input is my output going to be 0? So we need a quarter to the x minus 1 to be equal to 0. And so we're basically going to say that a quarter to the x needs to be 1, because 1 minus 1 is 0. And the only way that that can be true is if x is equal to 0. So actually, my sketch is off, because then that means that this guy needs to be over here. So at that point, I would actually quickly erase my sketch and redraw it and pretend that that didn't happen. Alright, there we go. There's my cured sketch and our x and y intercept all in one is the origin. And you can test that. Remember that the y-intercept occurs when my x is 0. So if I substitute 0 over there, I get a quarter to the 0, which is 1. 1 minus 1 is 0. So you have 0, 0, origin, boom, karabeam, karaboom. So there you go. That is the graph. And again, we want to talk about the idea of domain and range. So the domain of this function is also any real number. So there is nothing that you aren't allowed to raise a quarter to the power of. So a quarter to the power of 2, a quarter to the power of -1, a quarter to the power of 0, a quarter to the power of 2/3. All of those things are valid and defined. So those inputs are okay. They are not banned. So any number is allowed as an input. But what we see is that the range of the function is not just everything y. right? Again, it seems like the range is capped over here. The range of the function. So the possible outputs of this function are any number bigger than -1. So y can be anything bigger than -1. So we can see here that, you know, if you look for an output that's larger than -1, there is some input that is yielding that number. But down here, the graph doesn't exist. So the graph does not output any values below -1. Well, equal to -1 or below. So the range of the function is, the only outputs it produces are from upward of -1. Okay, let's see if we can squeeze in one more. Cool. So sketch the graph of g of x is equal to -3/x plus 5. And by virtue of that x being down here, the moment your input is dividing, then you definitely know that it has a hyperbolic. The graph is a hyperbola. And so again, we work from the basic shape, y is equal to 1/x. We think about what's happening there. So we know that, that looks like that. And then the first thing that's happening is we're saying, well, -3 times that 1/x. You think about, okay, what does that do to my graph? And then once you've done that, you then take all those outputs and you increase them by 5. So your graph is moving up by 5 units. So the sketch of your graph is going to look, typically it's easier to draw the asymptotes first. So we know that that asymptote is still in place. Nothing has happened to it. But because of this shifting up by 5 units, the horizontal asymptote has also shifted up, and remember to label that. The asymptote has shifted, and because of this -3, there's that reflection happening in the x-axis, because these outputs are now being multiplied by -3, so they're going to come over here, and these outputs are being multiplied by -3, so they're going to become negative and come here. So you end up with a graph that looks like this, right? And so again, if you asked what are the asymptotes of this graph, the first one is the y-axis, otherwise known as x is equal to 0, and the other one is, again, think about, okay, what's constant here? My x is changing, but my y is staying the same. So the equation is going to be y is equal to 5. So those are your two asymptotes. And then, what do I want to say? Oh, we need to work out that x-intercept. Obviously, there's no y-intercept because your y-axis is an asymptote, so your graph is not going to cut the y-axis. So x-intercept, we know that my y is equal to 0. Can you try to solve this equation for yourself? Which input, is going to give us an output of 0? So pause the video and try to work that out. Righties, so you should have gotten 3/5, and here on the right is a potential way that you could have gone about solving the equation. That is an x over there, very terrible looking x. And so that would be your graph. And then again, or another thing you might be asked is the axes of symmetry. So y is equal to 1/x has two axes of symmetry, y is equal to x, y is equal to -x. And so if you move the graph up or down, then the axes of symmetry will also move up or down. So in this case, your one axis of symmetry will be y is equal to x plus 5. And your other axis of symmetry would be y is equal to -x plus 5. So both of them just move up the same way that your hyperbola moved up or down. But important thing to discuss here is the idea of domain and range. So unlike the other functions that we've looked at, this function does have one particular input that it is not fond of, and that input is 0, and that is why x is equal to 0 is an asymptote. It's, you know, that input is not allowed because division by 0 is not defined. So the domain of this function would be x can't be 0. X is not allowed to be 0. And so if you're asked what the domain of the function is, that would be your response over there. And then likewise, you might be asked about range. And if you look at this function, again, there's a whole range of outputs, but there's one output in particular that this function will never produce, and that is 5. So remember how this asymptote means that the outputs are getting closer and closer and closer and closer to 5, but they're never actually going to be 5. And likewise over here, you know, your outputs get very close to 5, but they're never actually 5. But otherwise, it produces every other output under the sun. And so your range is going to be that g of x will never be equal to 5. So g of x can be anything except 5, really. So so that's how you'd answer a question about what the domain and the range of the function are. Yes.